Okay, so hello everyone. I will present today the work named ProFlow, Learning to Predict Optical Flow. It's a joint work with my supervisor, Andres Brun from the University of Stuttgart. So let me start by giving you a small recap on what is optical flow. So we're given typically an image sequence, and for any two consecutive frames in this image sequence, we want to compute a dense interframe displacement field between these two images, which is also known as the optical flow. Now, many recent approaches are limited to the use of only two input frames. This means that temporal information on temporal coherence cannot be exploited by the algorithms. And reasoning in occluded areas is solely based on regularization. However, by considering multiple input frames, it enables us to exploit information on temporal coherence. And this can be very beneficial in the context of occlusions or elimination changes. But the question is, how can we use these multiple input frames? And to do this, we somehow have to relate multiple displacement fields with some sort of motion model that describes how the motion varies over time. But finding a suitable motion model is a non-trivial task. In the literature, different motion models have been proposed and used so far, like constant velocity models, constant acceleration models, parametrized trajectory models, or ego motion models. Now, the difficulty is here that not every model is suitable for every task. So, for example, in the ego motion model is only applicable in mostly rigid scenes and is only beneficial for the rigid background and doesn't really help in case of independently moving objects or non-rigid motion. And of course, if you use the wrong motion model to extract information from these multiple input frames, it can significantly deteriorate the estimation and introduce errors. Now, what we've done in our work, we've learned a motion model based on the CNN, and we trained the model during the estimation, so we apply a sort of online learning, and we do not require any ground truth data to train the network, so we train the network in an unsupervised way. And the actual model we learn is spatially variant, so it can handle multiple motion patterns and different objects within the same scene. Now, let's take a look at our approach. So our approach takes three input frames, a reference frame at time t, a preceding frame at time t-1, and a subsequent frame at time t+1. Now, in the following, with the term forward flow, I will refer to the flow field from the reference frame to the subsequent frame, which is also the actual flow field we want to estimate. And with the term backward flow, I will refer to the flow field from the reference frame with respect to the preceding frame. Now, we have this pipeline approach, and the first step is to compute an initial backward and forward flow using some sort of baseline method. Then we perform a bidirectional consistency check to remove outliers of these initial flow fields. And with these filtered flow fields, we then train our motion model. And with the trained motion model, we transform the filtered backward flow into a predicted forward flow. And these predictions are then combined with the outlier filtered forward flow. And finally, we in-paint and refine the combined flow field. Now let's take a look at the individual components we used within our pipeline. So our baseline method is based on the common optical flow pipeline, which consists of the four steps, starting with the matching step, an outlier filtering, an in-painting step, and a final refinement step. Now in case of the matching, we used coarse-defined patch match, which is based on SIF features. Then as an outlier filtering, we applied once more the bidirectional consistency check. And as for the in-painting, we used a robust interpolation of correspondences named RIG. And as refinement scheme, we apply the order adaptive illumination area refinement. Now let's take a look at the motion model learning. So as training samples, all locations where we have a valid forward and backward flow are potential training samples. So these locations surpass the outlier filtering test. Now, as input from the training samples, we extract several 7x7 patches, which includes the backward flow components, the U and V, a valid flag, and as well the spatial location within the image domain. And the output of the training samples is simply the forward flow vector, which we would like to predict. Now with these training samples, we then train a small regression network architecture which map these backward flow patches to a forward flow vector. And it's a quite small network which only consists of 2 convolutional layers where each has 16 3x3 kernels and 1 fully connected layer. And with this trained network, we can then compute the predicted forward flow, and which we then have to combine somehow with our initial forward flow field. And this is done in a quite simplistic manner. So we simply augment the filtered forward flow estimates with the predicted forward flow. So we just fill in all the locations where we weren't able to get a good estimate for the filtered forward flow with the predicted flow vectors, as we can see in this image. And of course, it can happen that some locations we don't have any estimates at all. So we once more inpaint these areas using, again, the rig inpainting as in the baseline. And finally, we apply once more the order adaptive illumination area refinement. Here are still some small details on the refinements kept. So it basically locally selects the most appropriate regularization order. So it can not only handle frontal parallel motion, but also affine motion. And in addition to the flow, it also estimates illumination changes. And this allows the refinement step to keep up with the invariance of the underlying feature descriptors, which may be employed in the preceding matching step. And another difference to traditional single level refinement schemes is that we still apply a reduced coarse to fine scheme, which enables the refinement with some sort of error correction capability. So after we've seen now all the individual components of our pipeline, I would like to show you some results. But first, I give you some brief details on the parameter setting. So in the original parameter setting, we already had a single of the default parameter set for all the benchmarks in case of the matching step, the inpainting step, the filtering step, and the learning procedure. And we only had a different parameter set in case of the variational refinement, which are basically 3 parameters which differ in the estimation. And of course, we had to let the 3 varying parameters fixed to fulfill the ROB challenge requirements. And we've done this simply by minimizing the bad pixel error of the baseline method on a subset of the training data. So next, I would like to show you some visual results. So on the first row, we see the 3 input frames. On the left, the preceding frame. In the middle, the reference frame. And on the right, the subsequent frame. In the second row, we see on the left the areas where we included predictions. So these are highlighted in orange, and blue are these filtered forward flow vectors. Next to it, we have an error visualization of the baseline and our approach, where dark blue means a perfect estimate, and as the color varies over white to dark red, the performance decreases. And in the bottom row, we see the ground truth flow field, the baseline flow field, and the flow field of our approach. Now in this scene, as we take a look at the reference image, we have here this dragon and the person, and between these 2 objects, there's a small piece where we see the background in the reference frame, but it's occluded in the subsequent frame. And in the baseline method, we have a huge error here. And by including these predictions within these areas, we can improve quite a bit. And we can also see that the flow estimate is then correct in this area. And we get nicer boundaries around the head, and we have a nice contour of the leg of the person. The next sequence shows the benefit in non-rigid, in case of non-rigid motion. So here we have this hand which grabs up this bar or whatever. And we can see in the baseline that the fingertips are not estimated quite good. And we improve by once more including predictions in this area compared to our baseline method. The next type of scenario where we can improve is in case of illumination changes. So we have here this dragon running over the marketplace. And as we can see here, it runs from a sunny region into a shadowed area. And we get these strong illumination changes on the head of the dragon. Now, in case of the baseline method, we are only able to capture we are not able to capture the entire head or the motion of the head quite well due to the strong illumination changes. Now, once more, by including these predictions, we can improve quite a bit on the head of the dragon. Now, next I would like to show you some quantitative results on the training data of different benchmarks. So what we see here first is the performance of the baseline method, and where we swapped or changed the individual components of the classical or common optical flow pipeline. So we're starting with the epic flow approach, and then we exchange the deep matching with the course-defined patch match, and we can see we already improved quite a bit. Then if we further exchange the in-painting step with from the classical epic in-painting to the rig in-painting, we improve even further, except for the scintille benchmark in this case. And in contrast, if we don't exchange the in-painting step, but the refinement step, we even improve a little bit more. And finally, if we change all the three components, we get the best result, which is the baseline we used in our approach. So the baseline we use already outperforms all the individual components proposed in the other works here. Next, I would like to show you some results for the prediction. So here we have comparison to a constant motion model. So basically, which just swaps the sign of the backward flow to get the forward flow. And we can see that we get huge error values, and we can't really use these to get anything useful. In contrast, our learned motion model gets very good estimates. And in case of the Kitty benchmark, we even outperform the baseline approach, which can be explained due to the high regularity in this benchmark, where we have this forward motion all the time, and the boundary areas of the image move outside the image domain, so we can't really find the correspondences. But with respect to the preceding frame, we still see these areas, and we can actually compute estimates. So the learned motion model clearly outperforms the constant motion model. And finally, we have still the quantitative results for our full approach. And as we can see, compared to the baseline method, we improve, we get a constant improvement, which ranges from 8% on the scintille benchmark up to 27.5 on the Kitty 2012 benchmark. So we have this clear improvement compared to the baseline. So what we have here next is some results for the test data. It's basically a copy of the ranking table from the RUB challenge from the website. And in addition, we added in brackets the actual ranking on the online benchmark tables, which consider all the approaches which are uploaded. This includes also non-anonymous methods, but excludes, in case of the Kitty benchmarks, is the method which use stereo image pairs. And as we can see here, we get a quite good performance on Middlebury with rank 14, on Kitty 2015 with 18, and rank 3 on the final render pass, and rank 2 on the clean render pass of scintille. And what we have to keep in mind here is that the other approaches which have uploaded here, excluding the RUB uploads, do not have a single parameter set across all the benchmarks. So we also get a good ranking compared to all the other methods which are available online. So finally, I would like to summarize my talk. So we have a 3-frame pipeline approach, which includes a motion model learning step and a prediction embedding step. And the learned motion model is basically a spatially variant mapping from the backward flow to the forward flow field. And we learn an individual model per frame in an online learning. And we've trained the network in an unsupervised manner, so we don't require any ground truth data to train it. And regarding the results, we can observe an increased robustness, especially in the case of occlusions or illumination changes. And we also get improvements for non-rigid motion. And finally, we also get consistently good results on all the major benchmarks. So thank you very much for your attention. I'm happy to answer any questions.
Thank you very much, and we again have time for questions.
I have a question. Thank
Yes.
you for your talk. So for the occlusion estimation, you used a forward-backward check?
Yes, but like not not the forward and backward flow like I told here. It's like we have to compute an additional flow field with the swapped images.
This makes more sense. Otherwise, you would have a constant velocity assumption that
yes,
just
exactly.
learn the constant velocity.
Yeah. So for this bidirectional consistency check, we have to compute an additional flow field. So actually, we have to compute 4 flow fields for the initial flow estimation step.
I have one more question. So for the training of your motion model, you use just the output of the method, right?
Yes, exactly.
Did you try to use, since you have it, ground truth, and then maybe refine it with the output of your method just to get a better initialization and better results?
No, we didn't try this. So basically, we could do this. So in the ground truth, you typically only have this forward flow field, and you would have to compute the backward flow field like by making this alignment. So in our approach, since the reference frame is the same for both flow fields, so we don't have to have this problem like to find the corresponding flow vector. Like we simply look at the pixel location and we directly get the forward and backward flow vector.
For Sintel, you could use in the non-occluded region actually the 2 flow fields that you have, like in the past and in the future, and just invert it, I guess.
Yes.
Thank you.
Yep, thanks.
As I said, we have plenty of time for questions.
Yeah, maybe I can add still something to, like, with respect to the first talks, like we had a lot of talks which address the problem like of occlusion identification, and this is like maybe an idea like how to improve in these occluded areas. So like basically this outlier filtering step is just here to like identify like mainly occluded regions. Of course, not only occluded regions, because like as we have seen, we can also benefit in like problematic scenarios where we have these strong illumination changes. But this is also something which could be combined with ideas from the other works, like to fill in this gap, like, okay, we now identified areas or regions where we cannot get good estimates, and this could be a work which addresses the problem, like how can we improve in these areas then?
I have a couple of questions.
Okay.
So you are looking at 7x7 regions around a pixel when you do the flow field prediction. Have you looked at, considered using larger field receptive fields?
Yeah, so we tried out different sizes, but we started like with single pixel levels. That didn't work as well, but it worked. But we didn't try a lot larger areas because then you depending on like you get mixed objects within this image patch. So I can't really tell if it like gets a great improvement or if it like the improvement decreases. Like you definitely like if you have depends on the object sizes within your scene or the image. So if you have large objects, it definitely can help. But if they're small, it could get problematic.
When you train your the optical flow, did you consider training it over multiple frames because you're doing the motion prediction over multiple frames? Could this help with the initial optical flow predictions?
To change the baseline already? Or
yeah, to consider more than 2 frames.
We haven't done this so far, so we only limited to this 3-frame setting.
Are there any questions from the audience?
What's the FPS?
What's the frame rate at which you can run this?
So roughly we take the overall approach, I guess, like depending on the image size, like for a kitty image, I think it was like around 2 minutes. So, but it depends on the individual components you use.
Then let's thank the speaker again. We'll have a lunch break now and we'll continue at